and also I'm going to share some problem sets with the colleges so that they can use that for. We'll also solve those problem sets and we will actually use that for discussion. Okay, and I'm sharing my keynote presentation. Okay, um, let me know if you're able to see this. Are you able to see the desktop? Okay, so I will sort of now. Um, okay, so if there's anything, please call me on my phone. If you're not receiving anything, since I've now moved into the PowerPoint presentation, I won't be able to see the. Okay, I'm using the keynote. I won't be able to see you. Okay, the desktop is on now, so I won't be able to see the thing. Okay, so you have to call me on the phone line because I won't be able to see anything except my slides. Okay, Chakravarti, if there's a disturbance in the transmission, either you or no, this thing, Ramakrishnan should call me mobile. Okay, right? Just use the no SMS to say yes to me so that I know you're able to hear me. Okay. Can you just respond with an S on the SMS, please, on my phone? Is everything coming now? Is the desktop running on functional dependencies? Can you see that? You won't be able to see me, but then you'll be able to only see the Just respond. Chakravarti, can you just respond to my phone by an S? Yeah, okay. So if there is any problem, just please ping me on the phone. Okay, phone line. I'll be only on the PPT mode. Okay. Yes, okay. Yeah. Fine. So basically, we have been doing the functional dependencies in the last. Okay, and then we are I've tried putting all of what I've been doing on this so that it becomes clear. I'll also share these slides with you. Okay. Since the board we have some problem, I thought I will put everything on the slides and then sort of give you the slide presentation. Okay. Now, as you can see, a relation R, okay, a relation is characterized by a name for the relation and a set of attributes. As you can see here, A, B, C, D, and E. Okay, there are 5 attributes. Okay, right? We saw this in the first class itself. Now, functional dependency is two tuples. Okay, U A1 B1 and V A2 B2 belonging to this relation R. What this means is if A functionally determines B, what this means is if U of A1, they agree on A value, both U and V agree on the A value, they will also agree on the B value. U and V also agree on the B value. That means in this relation R, A to B, if there is a functional dependency between A to B, if the value in the tuples, if the value of A is same, then the value of B is also going to be the same. That's what we mean by the functional dependency between the attributes. Okay. Now let us see an example here. Okay. For example, here there is a student relation. Okay. The name of the relation is student. Then we have 3 attributes: roll number, name, and GPA. Okay. Each of these attributes takes values over a domain. Right. This is also what we have seen also in the previous. Okay. Roll number, for example, is a alphanumeric, 7-digit alphanumeric value. Okay. Alphanumeric string. Okay. Name again is some characteristic. GPA is a float. Okay, right? These are the domains where where each of these attributes taking a value. Now, if you take an instance of this relation R, student relationship, U is one tuple and V is another tuple. Okay. Now, what this is saying is the U instance of this tuple, the roll number of the student is CS16D002. Okay. The name is Ramya. Okay. And GPA, that is the actual what's the percentage of obtained by the student in exam. Okay. So 8 is what is the GPA. Okay. Now, as far as another instance of the student relation tuple, so this also has C16D002. So if they agree on the roll number, okay, if they agree, these two tuples U and V agree on the value of the roll number, in this case CS16D002, okay, both of them have the same value. Okay, if they agree on this value, they have to agree now on the name and GPA. If this is the case, we call roll number functionally determines name and GPA. Okay, this is what is the meaning of functional dependencies. Okay, right? Between the two tuples, roll number now determines name and GPA. If two tuples agree on the roll number, they have to agree on the both the name and the GPA. Okay, this is what we mean by functional dependency. This is an example of the functional dependency. As given in the previous slide. Okay, for example, here this is the slide that we had given, first slide. Okay, if A determines B, A functionally determines B, we gave it in an abstract way. There U and V are two tuples belonging to the relation. If they agree on the value of A, they have to agree on the value of B. Okay, I am pretty today just to make sure that all of you understand this important concept. So I am repeating, making sure that whatever I am teaching completely is understood by all the students. Okay, and also I am speaking very slow so that the English sentences can be understood by the students. I sort of realize that English may also be a problem for the students. Okay, so I'm speaking very slow, making sure that the students can understand what I'm saying. Okay, right? Hope this is clear. Okay, right? Another thing this time is, since I've gone into the presentation mode, I am not actually seeing anything on the. Please understand that I'm in the presentation mode. Nothing else is visible for me on the A view. Nothing is visible. So even if you're putting anything on the chat box, I will not be able to see in the course of the presentation. But I'll take a break at some point and then ask questions, or I'll see if you have any questions. Okay, right? So okay, now. For example, it is not a functional dependency. For example, name, two students could be having the same name, okay? But then it doesn't mean that their GPA will be the same, okay? Number means that it's the same student, but name same means it need not be the same student. Two students can have the same name, okay? Not true functional dependency, because two different students can have the same name. Now take this case of U and V of the student relation. U, CS16D002, name is Ramya, GPA is 8.0, okay, is the GPA. V is another tuple belonging to this relationship, okay. Now here the student roll number is different. Please see that there is a difference in this roll number. CS16D008, okay, but the student name is same, Ramya. There are two Ramyas, but they are different. They are not the same Ramyas, okay, because the roll number is different, okay. Obviously, then they need not agree on the GPA. As you can see, name determines GPA is not correct. Ramya doesn't determine, the name doesn't determine the GPA value, because in one case, one Ramya got 8 CGPA, another Ramya got 7.5 CGPA. Okay. So in this case, U of name, the first tuple's name equals to the second tuple value, name value is equal, does not imply U's GPA value will also agree with V's GPA. GPA value, in which case no dependency. Okay, name doesn't determine the GPA value in this relationship. Okay, this is how we will look at functional dependencies. Okay. Now, if you make an assumption that names are going to be unique in my no students in my college will get the same name, I'll ensure that. Okay? That's no, not practical. But if you make that assumption in the domain, in your college, for example, if you make an assumption that two students will never get the same name, okay, then you can say name determines the GA, because whenever, since you are making this assumption, like the roll number is unique, okay, similarly you can also make an assumption which is not a practical assumption, so you can't make that assumption, no, strictly speaking, on this data. Okay, if you make that assumption, then you can say name determines the GPA. Okay, so functional dependencies are given by the domain. For example, if your domain says that name doesn't determine GPA, it means that it is allowing the different people to have the same name, which is a practical. Okay, right? But then your domain says that no, student roll number will never be the same for two different students. Student roll number will always be unique. For example, CS6D002 will be given only to one person. It will be unique. Okay. Two different people may have the same name, but then their roll numbers will always be different, because that's how your domain will work. Domain will clearly give a different roll number for two different entities. There are two different students. They are going to suddenly get two different roll numbers. Okay, and also, so this is what we understand by functional dependencies. Okay. After this slide, it should be clear for you what is a functional dependency and what is not functional dependency. So given a relation, at the end of this slide, you should be in a position to say, given a relationship, you are able to identify the functional dependencies, okay, in the relationship. That's what we expect you to understand at the end of this slide. Okay, right. What are functional dependencies? We'll go further deeper on this. Okay, they come from the domain. Okay, what determines what comes from the domain. Okay, for example, identify the functional dependencies in the following relation. The relation is, we have city, state, and capital. Okay, for example, one instance of this relationship is U is Kakinada. No, state is Andhra Pradesh, AP, and then capital is Amaravati, the new capital of Andhra Pradesh. Okay. Similarly, there is another instance of this V, okay, which is Rajahmundry. Okay. Then again, it is Andhra Pradesh. The state is Andhra Pradesh, and the capital is Amaravati. Okay. UV J or something like that I should have put. I made a mistake here. It should be J. It's not another instance of the relationship. Okay. The city is Chennai, state is Tamil Nadu, again capital is Chennai. These are the instances of this relationship are city, state, and capital. Okay. Now, how do I determine the functional dependencies? Okay, between the various attributes in this relationship. Okay, right? Now, if I want to determine determine the functional dependencies in the relation. So we have to make some assumption. Okay, one assumption that we can make, which is normally a true assumption, is assuming that no two cities have the same name. Every city has a unique name. Okay, then every city having a unique name will determine the state to which that city belongs. So city determines the state. This is one functional dependency. Okay, city also determines capital, because if you say city, then you know the state and also the capital of that state, and you assume that only one capital state. By this assumption, also will. Okay. state determining the capital. Okay. Now, what are the functional dependencies? City determines state and capital. State determines the capital. But you may not want to say, put this functional dependency saying that the capital determines the state, because it is possible for two states to have a common capital, like Chandigarh. Chandigarh is a common capital for the states, right? So basically, you have it's a shared capital. Okay, it's a shared capital between the two adjacent states, right? So basically, right now I think we can say in some sense Hyderabad is also a shared capital between the two states of for a while, going to be a shared capital by both Andhra Pradesh and Telangana, right? So you can't say capital means given a capital city you can determine the state. It can be anything, right? It can be one of those states. So you can't actually determine. This functional dependency doesn't hold. Okay? But the other functional dependencies hold. City to state and city to capital. Okay? So given a city, you can determine the state and the capital. Okay? These are the functional dependencies that are there in this relationship. Okay. Okay. Now take this example of, I will give some instances of this and see what are the kind of things that we are interested when we take a relation and look at the functional dependencies. For example, in this case, the city is Vizag and the state is Andhra Pradesh. Then I put the capital back to Hyderabad. Of course, right now it's Hyderabad, right? And it's going to be Amravati or it's Amravati. I don't know. Just started, right? Then Kakinada, again Andhra Pradesh, and then Hyderabad. Hyderabad, again the state is Telangana, and then it's Hyderabad. Okay. Then Rajahmundry, then Andhra Pradesh, AP, and then Hyderabad. So these are some of the instances of this city, state, and capital. Okay, right? Given those kind of functional dependencies. Okay. Now this is also given in terms of the table format, as you can see. City, state, and capital. Visible. The relation is like a table. The first row in the table is basically the attributes, and after that, the actually values of those attributes. Okay. So each of these rows are called the tuples. Tuples of the relationship R. Okay. Now, if you look at this, is since it's a set of tuples. It doesn't matter if I keep Rajahmundry first, Vizag later, or Kakinada first. So the order doesn't matter. Similarly, relation has a set of attributes. So it doesn't matter if capital is first column and then city is the last column. It also doesn't matter. Okay? These are some of the things about the relation. A relation is a set of attributes. Okay? And then there is a set of tuples. So it doesn't matter. Okay? Since it's a set, you cannot have repeated, same elements repeated. For example, you are not going to have another tuple which agrees exactly with on all the values of another tuple. For example, we can't have another row where you say Rajahmundry, Andhra Pradesh, Hyderabad. It exactly agrees with already existing element. So you can't put duplicate rows, exactly having the same values. You can't put two duplicate rows. There's going to be only one. There's no duplication. In the set, there's no duplicate elements allowed. Okay. So the relation considered here is a set. If you consider relation as a bag, then you will be able to allow duplicate values in the in the set. Okay. Right now it's a set. It is not a bag. Okay. The relation is a set. Relation is a bag. Then I will be able to consider another element which is Rajahmundry, AP, and Hyderabad. Right now, keep that away. We'll only consider the set relation as a set. Okay. Now, what are the problems with this? With this? Now, if you look at when the capital of AP is changed to Amravati, then we need to update the fact in 3 locations in the table. For example, you can see the fact that AP's capital is Hyderabad is repeated 3 times in this table. You can see You have Vizag, AP, Hyderabad. Kakinada, AP, Hyderabad. Okay, Rajahmundry, AP, Hyderabad. Okay, there are 3 cities belonging to this state, and then right now the capital is Hyderabad, but then now it got changed to Amaravati. Okay, when the capital of AP is changed to Amaravati, we need to update this fact in 3 locations in the table, not just 1 location. Where all it appeared, you have to go and then start changing at all those places. This is because we'll see why this is happening. Okay. Now you don't want to do this. For example, at one place you have changed it the capital. You have to now make sure at multiple locations this is changed in the in the table. Okay. In the database design, the golden rule is one fact at one location. The fact that AP's capital is Hyderabad is stored only at one location. The minute this fact has changed, okay, there is an update on this fact saying that AP's capital is now Amaravati. You just need to go and then change only at one location if you follow the golden rule. This is suddenly not following the golden rule. This is now getting repeated. This information, this fact is getting repeated in the table multiple number of times. So this is a bad way of designing your relation, because this relation is suffering from what is called duplication. It is getting duplicated. The same fact is getting stored multiple number of times. There is duplication in this relationship, okay, which is not a very good design, database design. Okay, you want to actually change to say that yes, this is going to be only this information will be stored only in one location, not at multiple locations. Okay, this can be achieved. Okay, now you can split the data and the relationship. Now you can split the relationship into 2 relationships. One is the state and the capital. The other is the city and the state. Okay, now you can see Vizag is Andhra Pradesh, Kakinada is Andhra Pradesh, Hyderabad is Telangana, Rajahmundry is Andhra Pradesh. So I put this. Now, in terms of state and capital, you can see Andhra Pradesh capital Hyderabad, Telangana capital Hyderabad, Tamil Nadu capital Chennai, Kerala Trivandrum. So I'm just storing this. Now, if I have to change the fact that AP's capital has changed to Amaravati, all that I have to do is go to the first row of the state capital and just change the capital there. Whereas in the previous case, I'm going and then doing this change in 3 places, 3 locations. When I've combined this relationship and kept all this data together, and going and making changes in 3 locations. The minute I'd actually split this into 2 relations, okay, and I got this whole thing right, because there's no duplication. If you look at this whole table, 2 set of tables here, nothing is duplicated here. Okay, everything is represented only once. Vizag belonging to Andhra Pradesh is represented only once. Okay, similarly Kakinada belongs to the state of Andhra Pradesh, again is represented once. Hyderabad belonging to Telangana is represented once. Rajahmundry belonging to Andhra Pradesh again is represented once. Similarly, the state capital information is also represented once. If you look at this whole thing, the golden rule is, given a database design, you want to store the data into these tables. The golden rule is that you want to actually store one fact at one location. Okay. Now, each of these facts are sort of brought out by each functional dependency states a fact, okay, in some sense. Okay, now go back to the previous previous slide, okay, and then previous slide. Here is the functional dependency. City determines the state, okay, state determines the capital. These are the 2 functional dependencies. Now what happened? If these functional dependencies are not taken care properly, you actually end up the facts getting repeated. For example, the state capital information is getting repeated here, as you can see, because of some reason into this table. Okay, so that's what we want to avoid. Each functional dependency, when we look at a functional dependency, each functional dependency is representing a fact. Okay, now your idea is each one of that you want to represent only once. if you want to represent in this table only once, each functional dependency as given here, as you can see here, each functional dependency as given has to be a key to the table. Key means that it will not get repeated. We'll just come to that in a minute. Okay, right? So what are the problems with the previous one? Duplication. State and capital information repeated several times. This is a problem. Okay. Update anomaly. When the state capital changes, AP from Hyderabad to Amravati, and this is not changed in all the places, there will be an update anomaly. In 3 places, let us say we changed it, but then we forgot to change for Vizag this information, then Vizag will reflect a wrong information that Andhra Pradesh capital is something else. Deletion anomaly. For example, here there is some information on the Tamil Chennai, right? Basically, I think there is one which is talking about this Chennai, Tamil Nadu, Chennai. Okay, this is the only city that is there. Let us say for some reason I end up deleting this record, Chennai record. Then along with this from the table goes the information that then Chennai's capital is Tamil Nadu's capital is Chennai. That fact is also lost. Okay, so this is called actually the deletion anomaly. Okay, this is what we mean by the deletion anomaly. When the last city from a state is deleted from the table, the fact that there is a capital for the state is also deleted. These are the 3 problems with the relation that we have here. The initial relation that we started off. Okay, our city, state, and capital with the functional dependencies that we saw. Okay, right? We want to suddenly avoid these. That's where basically to avoid these problems, functional dependencies have to be taken care of properly. Such a property is often called the normal forms. Okay, a relation in a proper normal form can avoid problems due to duplication of. For example, if you bring the relation into a proper normal form, then all these problems due to duplication of facts can be avoided. This is very easy to understand. Once you get this concept clear, you will be able to understand it. Okay, in easier sense. Okay, right? Okay. So what are the normal forms? Now we will move on to normal forms. What is it that we want to understand, want you to understand at this point of time? First, we want you to understand functional dependencies. Okay, the first set of slides are actually making you understand where we started in the functional dependencies. First few slides are trying to make you first understand what is a functional dependency. That's what, by the end of this slide, you should know what is a functional dependency, what is not a functional dependency. Okay, from this point onwards, using the city, state, capital, we want you to understand what kind of problems the functional dependencies will cause. Okay, for example, here being, if there is a functional dependency, it is possible that duplication can occur like this between state and capital. If the functional dependency is there, it could cause the duplication of the data. Okay, and this is where we are saying that this can cause duplication problem, update anomaly, and deletion anomaly. So this is the reason why functional dependencies in a relation have to be taken care of. This is what we want you to understand by the end of this slide. Okay, this is the concept that we want you to understand. Okay, now to avoid these forms, we will start seeing how to avoid these problems. How do we design our relations using the normal forms? Okay. Now, before we get on to normal forms, we'll also understand the concept of keys and superkeys. Okay, given a relation R having a set of attributes A1 to AN, some set of attributes A1 to A1. For this relation, we say a set of attributes AI to AJ is called key if it identifies uniquely the tuple of the relation and not any of the subsets of the AI to AJ. Which means that how do we identify uniquely the tuple in this relation R, right? And what are the set of attributes that uniquely identify the tuple? Okay, we'll see an example for this. For example, what is the in the relation R, city, state, capital, what is the key to this relationship? If you assume city name is unique and two cities will never have the same name, then city uniquely identifies every tuple in this relation, and hence it is a key to the relationship. Okay. What does that mean? City will never get repeated in this relationship. Vizag, Rajahmundry, Chennai, okay, Chandigarh, Delhi. Okay, you don't repeat the city name. City becomes unique in this tuple. Okay, if we assume that city name is unique and two cities will never have the same name, then city uniquely identifies every tuple in the relation, and hence it is the key to the relation. Now, if you assume city names will never get repeated within a state, but it's possible two cities, two cities can have the same name, but will be in two different states. They will not be in the same state. Okay. I don't know of a case where this is the case. Are there any cities in India having the same name? Before I come back here, let me go here and see what's happening in the AVU thing. Okay. Uh, okay. There is somebody else who is actually logged in from somewhere else. Okay. So before I go back to those slides, is there an example where two cities having the same name in India, but no, they are in the different states? Is there such an example? Is anybody knew such an example? I'm trying to make all my examples relevant for the people to understand. Okay, so everything is being only crafted for, especially since I'm teaching only Andhra students. All my states, city, state, capital was actually tailored to make them understand and appreciate. Okay, right. So is there a question? Somebody knows about any city having the same name? Two cities having the same name? Uh, Anybody has any? I just came out of the presentation. I'm just looking at the AVU chat. This thing. If you have any question, please put it on the. I also want to see if anybody has two cities with the same name. Knows the two cities with the same name. Okay. Has anybody got two cities with the same name? No, they don't know. Okay. I'm not seeing any this thing with that. Okay. So if you assume this is the domain assumption. Okay, this is the domain assumption. If you assume city names will never change. Okay. Okay. Uh, um, but cities will have the same names in different states. City plus state will uniquely identify all tuples in the relation. Okay, in which case city plus state is the key to the relationship. Okay, right? So it depends. What is the key to the relationship depends on how which attributes will identify uniquely the relationship. Okay, which attributes will uniquely identify the relationship R. Okay, suddenly key cannot be null. City having a null value does not make sense. Similarly, student roll number in a student relation, which is key, cannot be null. City, the key value, key attribute value cannot be null because that's the one which is identifying that tuple uniquely. Okay, right? But if there is a state for which there is no capital, then it's possible a newly formed state which still has not decided on its capital. The capital can be null. Okay, the value can be null. Okay, if state is the key, you can't have a null value for the state because first you have to identify the state. Okay, right? That's the key to the relationship. Similarly, here city is the key, So the value for city cannot be null. Okay, city value cannot be null. Right. What are super keys? Super keys are super keys contain keys. Otherwise, key is a subset of the super key. For example, if you have a relation R, A, B, C, D, if A is a key in the relation R, super keys are formed with the key. For example, A, B is one super key, A, C is another super key. Okay? A, D is another super key, A, B, C is another super key, A, C, D is another super key, A, B, D is another super key. A, B, C, D are all super keys for the relation R. Okay? Right? Anything that actually is formed the key, the superset becomes the super key. Okay? It contains the key attribute. Okay? Right. Yeah. One more example here. For example, take the relation movie. Okay? For example, if you take the relationship movie, then see that attributes are star, okay, then movie name, then studio name, and here could all be the attributes for this movie relationship. Okay. In the movie relation, if we do not allow star names to be repeated, then star the key. We assume in this case the star name will never get repeated. Okay. In this relationship, star will be uniquely identified by the star name. Okay, right? For example, there are not going to be two stars with the same name. For example, NTR in relation star, NTR will not be given. That name will not be given to another star. Okay, then in which case the star can be used. Star name key. Okay, name can be used as a key. If you also will not allow movie names to be repeated, but there are going to be multiple stars in the movie, movie name does not uniquely identify the movie record because there can be multiple stars. Given a particular movie, okay, there can be, we are not just saying hero, there are stars who acted in that movie. Okay, if there are multiple stars who acted in a particular movie, okay, then star name will not get repeated, but movie name, because stars acted in the same movie, movie name cannot uniquely identify the movie record here, movie tuple here cannot be identified uniquely by the movie name. Only star can uniquely identify the tuple. Okay, and hence movie name cannot be no, key for this relation. All supersets of star will be super key for the relationship. For example, star movie name, star studio name, star year, all this will become the super keys. But movie studio name cannot be a super key because it doesn't contain the star, which is the key for the relationship. Okay, so a super key is the one which is containing the key attribute. Okay, right. Okay. Now I'll also talk about trivial functional dependencies. For example, see this functional dependency, AB determines B. Okay. Now you can see the left side AB is determining B. B is a subset of the B is a subset of the right hand side. B is already there on the left side. It is also being put on the right side. This is trivially true because a tuple, U tuple, will always, if you take the B value, another another tuple, you also you take the B value. Okay, if they agree on A and B, they'll also agree on the B because B is part of this. Okay, right? This is trivially true, So we call this as a trivial functional dependency. This will be true. You can make any number of trivial functional dependencies. B trivially determines B. A trivially determines A. Okay, right? So for any given two tuples of the relation UV, if they agree on the left side, which includes the value of B, they also agree on the right side because they are already agreeing on A and they will agree anyway on B. A subset of this they are going to agree on because you are already saying that these two tuples on A and B, then it's going to anyway agree on B. So this is a trivially true, and this is called a trivial functional dependency. Okay. So what we want you to understand at the end of this, we want you to have the concept of what is a key to the relationship. Key uniquely identifies a tuple in the relationship. We also want you to understand what is a super key. A super key contains the key. Super key is the superset containing the key. Okay, right. And also we want you to understand trivial side is a subset of the left hand side. Okay, this is what we want you to understand. Okay. Now we get into the definition of the normal form, which is the highest normal form, which is a good normal form to avoid all the problems of the state capital, city state capital. Okay, we want to bring it to a normal form. This normal form is basically the Boy's card normal form, BCNF. In the simple form, it is called the BCNF. Okay, for every non-trivial functional dependency of the relation R. Okay, for every non-trivial functional dependency of the relation R having the set of attributes A1 to AN, the functional dependency is A1 to AM set of attributes determines a set of other attributes AM to AN. Okay, for every non-trivial functional dependency. When we mean by non-trivial functional dependency, we are avoiding this kind of dependency. This have no meaning. For every non-trivial functional dependency in the relation R, the left side of every non-trivial functional dependency in the relation has to be the super key for the relationship. This condition has to be satisfied for the relation to be in BCNF. If the relation is in BCNF, you can certainly say that no duplication is going to happen in your relationship. First, remember, we had this problem of duplication, right? When the city state capital, we had the duplication of state capital information. Okay. Now, what this is saying is, if this relationship is in BCNF, this problem would not have been there. That's what this is saying. Okay. Now, let us examine why this is so. Okay. We revisit the city data example. The relation R is city, state, and capital. Now we know that in this relationship, city is determining the state and the capital. Okay, and since we assume city names are unique, city becomes the key for the relationship. Okay, now state is certainly not a key for this relationship because state can be repeated. Okay, now you can see the left hand side of city. Left hand side of FD1. Okay, what we are seeing as a left hand side of FD1 here satisfies the left hand side of the left hand side of the FD1. Okay, what is the left hand side of FD1? City. Okay, city determines the state and capital. What is the requirement for BCNF? This fact, this functional dependency, the left hand side, if it is key to the relationship, it will never get repeated because that's going to be unique. Okay, so that ensures that the fact representing this functional dependency will not be duplicated because it is key to this relationship. City never gets repeated because it's unique. It is a key for this tuple, key for this relationship. It will never get repeated, and hence every functional dependency left side becomes the key for the relationship. This ensures there is no duplication at all. Why duplication comes in this relation? Duplication comes in city-state capital relation because the second FD2, which is state determines the capital, Andhra Pradesh has capital of Hyderabad or Amravati, is not taken care as a state being a key to this relationship. Okay, state is not key, and hence it gets repeated. Okay, state is key in this relationship. This would not have been repeated, and hence it would have uniquely identified, and this fact would have been recorded only once. Okay, FD2 is the one that violates the BCNF requirement. Since city is not the super key to the relation, there will be multiple cities in the relationship belonging to the same state, and state does not uniquely identify the tuple in the relationship, and hence state is not part of a super key, and hence this violates, okay, the BCNF requirement. Okay, BCNF is the highest form of functional normal form. BCNF is the highest form of functional norm. Okay, has to be, all that you have to see is left side of a functional dependency is a super key of the relationship, which means that it contains a key. Okay, key to the relationship. Okay, if this condition is satisfied, BCNF will not allow any duplication of the data to be happen. The golden rule that we stated in the beginning, that one fact at one location in the database will be achieved when the relationship is in BCNF. For the relation to be in BCNF, every functional, non-trivial functional dependency of the relationship, the left side of the functional dependency has to be a super key of the relation. Okay, if this satisfied, then the relation is in BCNF. Okay. One more example. This I did last time in the board. Okay, this one more example I did last time. So you have the property record. Okay, this is the house properties that are spread over in cities being recorded in this relationship. Okay, then we will give a unique identification for the property. For example, every property across all the cities will get uniquely identified with the property ID. So this property ID uniquely identifies the property record, and hence is trivially key to this tuple, key to this relationship. Every tuple will have a unique property ID. No two tuples will have the same property ID, and hence property ID uniquely identifies this property record, and hence it is key to this relationship. Then we have also the city in which the property is located. Then we have the house number. This house number of the property. For example, every city where the house is located, we'll give a unique house number in the city, okay, to identify the property. Okay. Then the area of the property, then price of the property, and tax of the property. Now let us assume that now let us assume that city, house number are also going to be unique. Okay, within a city, this is also a normal assumption that we can make, right? Given a city, the house numbers are not going to be repeated. Okay? Every city will have a unique house number. Two houses in the same city, we are not going to give name number. Uniquely identifies. So city and house number together is also a candidate key. So there are two candidate keys for this relationship. One is the property ID, and the other is city and the house number. So there are two candidate keys. There can be more than one candidate keys which uniquely identify the tuple. Here property ID can identify uniquely, so that's a candidate key. When you have multiple candidate keys, we will designate one of the keys as a primary key, so that the database understands that is the one which should be used while indexing, generation of indexes and all that. So we call that as the primary key. The other one becomes a secondary key. In fact, if you want to actually generate other indices, you probably will use the other attributes for generation of the other indices. When you say something is the primary key, the index is generated for accessing that table by the database based on the primary key. Okay? If there are multiple candidate keys, one of them will be designated as a primary key. Okay? Some of these we will see later. Okay? So this relationship can have more than one candidate keys. Okay? Right? There are two candidate keys for the relation property ID and city and house number. This is 8 keys for this relationship. What are the functional dependencies in the property record? The functional dependencies in the property record is property number uniquely identifies, okay, city determines, the functionally determines, okay, city, house number, area, price and tax. All other attributes are actually determined by the property number. This is one functional dependency. The second functional dependency, city and house number, also will functionally determine the property number, area, price and tax. Okay. We can also say city determines the tax. This is what we were discussing last class. I just put this in the formal thing. No, in my whatever I was discussing is putting them in the slides now. It took some effort and time to put them in the slides because I thought my board, no, I'm not able to wipe off the board, or no, focusing the board has problems. So I thought I'll put everything in for your sake. I was making these slides to make sure that everything comes in a slide form, and then so it's easy for you people to see it and follow. Okay, right? This is important, so that's why I started putting the whole thing in the slide fashion. Okay, right? Okay, then what are the other activities? It says city determines the tax. For example, Chennai has one tax, and then Mumbai has another tax, okay, and Delhi has another tax. So the city determines the tax depending on the city. For example, two houses are in Chennai, they'll have the same tax. Okay, city determines the tax. Okay, and then area determines the price. Given a particular area, we know this is the price that is going to be fixed, irrespective of the city, irrespective of the anything else. Now we'll just look at the house area, and then we say this is the price of the price is determined. The attribute price is determined based on the area. Okay. Now, if you want to examine, is this functional dependencies given this relation property record, which is this property ID, house number, area, price and tax, is this in the BCNF? Okay, these are the functional dependencies. So we have a relation and we have a set of functional dependencies. Okay, it's very easy to see. FD1 and FD2 satisfy the BCNF requirement since the LHS of both FDs are keys to the relationship. Go back and here look at property number, LHS, left hand side of this functional dependency FD1 is the key to the relationship. FD2, okay, the left hand side of the functional dependency, city house number, is also a key to the relationship. Okay, both these uniquely identify the tuples in the relationship, and hence they don't violate the BCNF requirement, which means the fact depicted by FD1 and FD2 will never be repeated in the relationship. Which are the things which are going to get repeated? For example, if you go to FD3 here, city is not a key to the relationship of the property record. City can get repeated, which means the fact that city determines the tax. Chennai has some tax, Delhi has this tax, will get repeated. Like what we saw, state and capital information getting repeated. The city and tax information data will get duplicated. Now, like the state capital has changed, if a city changes its tax, then this relation, you have to go to multiple places and change the data, okay, saying that the city is determining a particular tax. Same problem with area determining the price. So if you look at this relationship, FD3 and FD4 does not satisfy BCNF requirement since LHS of both FDs are not for keys to the relationship, and this relationship is not in BCNF. You can say this relationship is not in BCNF. Okay. So what is the BCNF requirement? BCNF requirement, all non-trivial functional dependencies in the relationship have to satisfy the condition that LHS of the functional dependency has to be a super key for the relationship. If this is not satisfied, the relationship is not in BCNF. Okay. I want you to understand at the end of this how to determine if a particular relationship R is in BCNF or not. If the relation satisfies the BCNF requirement, which is the Boy's card normal form requirement, then which is the highest normal form that is possible with functional dependencies. Okay, right? It is the highest normal form that is possible with functional dependencies. It will avoid any duplication of data. Okay, uh, hence, since it avoids any duplication of the data, it will avoid update anomalies and also deletion anomalies for the relationship. Okay, right. Okay, this is what we want you to understand. Okay, for example, how do you make this into BCNF? The previous one, which is not into BCNF. Okay, we need to split the relation to some. It cannot be one relation. For example, in this case, the property record, we take off the functional dependencies that are violating the BCNF requirement. There are two functional dependencies that are actually violating the functional BCNF requirement. For example, property record, property, city, house number, area becomes one no relation. Tax record, city and tax becomes the other relation. Price record, area and price becomes the other relationship. In this, you can see the first relation now is in BCNF because the only non-dependencies are property number determines city, house number and area, and then the other dependencies, city and house number, determines the property number and area. Both FDs satisfy the requirement of BCNF that no, the left side is actually key to the property record. The second relation, tax record, city determines the tax and city is the key to this relationship. City will never get repeated. City will be represented only once in this record. So city uniquely identifies the tuple, city and tax. So city is the key in this relationship. So the dependency city determines the tax, again satisfies the BCNF requirement that the left side of the relationship is uniquely determining the left side of the functional dependency is the relationship super key. Okay, same case with price record where area determines the price. This functional dependency, the left hand side is actually the super key for the relationship, key to the relationship, which is same as it also means that it's a super key. Okay. More on functional dependencies and keys. For example, we are going to look at trivial. I'll be going little deeper from this point onwards on actually looking in an abstract sense the relations and seeing how we are going to look at relations and functional dependencies and also look at the other normal forms. Let me see if how we are doing in the A view thing. Okay. Yes. I think there is a chart here. Yeah. Yes. Okay. Are there any questions at this point of time? I think I've already sharing the desktop. Is there a problem with the desktop, Ramakrishna? Is the desktop coming up? Is my presentation visible? Ramakrishna, is the presentation visible? Is it coming? Yeah, I think, yes, okay. So we will wait. I'm just trying to get back to my slides again. Okay, more on functional dependencies and keys. Okay, so if you have a basic thought, A determines function B, the aggregation rule says that AC also functionally, no, if you actually augment the left hand side and the right hand side, it is also true. Okay, AC functionally determines the BC. Okay, right, because you've added C, they will agree anyway on C, since the no, initial dependency requirement requires that if they agree on A, also agree on B. So AC will functionally determine BC is something that is going to be true. Okay, right? If A functionally determines B, A functionally also determines C, it's equivalent to actually writing A functionally determines both B and C. Okay, the right hand side can be, trivially put together. Okay, this is also a simple requirement here. Okay, now if you look at transitivity, A determines B, B determines C. Transitively, if A is determining B and B is determining C, then this is equivalent to saying A also determines C. Okay, A also determines no, C, because transitively, if you take two tuples, A will fix the value of B. So because the two tuples agree on A value, they will agree on B value. The second one is saying that if you agree on B value, you will also agree on C value. So given this, the two tuples will also agree. Given they agree on A value, they will also agree on C value. This is called transitivity. Okay, the functional dependencies are transitive. Okay, given A determines the value of B, B determines the value of C, A also determines the value of A functionally determines the C. Okay, C attribute. This is called transitivity. Okay. Now let us look at the closure of attributes, because this is how we can look at, given a set of functional dependencies and a relation R, we can define a closure of attributes. Okay. Now what is the of attributes? Given a relation R, having the attributes A, B, C, and D, and the functional dependencies of this is an example case, right? We are talking about the functional dependencies in this relationship. Okay, A and B determining the value of C, C determining the value of D, D determining the value of A. These are the three functional attributes. Okay, right? That are there in this. Uh, these are the three functional attributes that are there. Okay. Now, if you take, for example, okay, uh, a, an attribute set on the left side and wants to find closure of this attribute set. This closure is depicted by a plus. This plus should be written on the top. Okay. Since I don't have an easy way of, I'm just writing it plus here. The plus should be at the top of the bracket here. Okay, that's what we mean by a closure. Okay, now what is the closure? The closure is, given this left side, this you have to understand a little carefully. Okay, I will actually use, I've not put all the things that go into the closure here. So basically, I'll take the, I'll just go to my board and then I will go on to the board. Okay, please permit me to actually go on to the board as far as the closure is concerned. Okay, and then come back to my slides. Okay, I have not put all the. I'm making these slides actually, or I will just give me a minute. Deeper on this, as am I still sharing the desktop? I think I'm sharing the desktop. Okay, I've not stopped sharing the desktop. Okay. Uh, I'll share these slides with you, so there is no problem sharing these slides with you. I'll share the slides. So this will be sent to all the college teachers, so you can also look at and take it from At the end of it, I'll also will have some no problem sets that you can look at, okay, and solve some problems. And I'll actually solve some problems for you in the next class. I'll do some problems in the class itself, okay. Okay, what is the closure? We'll do the second one, okay. We are starting with A and B, okay. Now we will see which are all the functional dependencies which satisfy the left side is in the set that I have taken. For example, if I have taken A, there is no dependency set in the functional dependencies that I have. AB determines C, C determines D, D determines A. The left side, none of them has J. Okay, there's both A and B determining C. So I can't actually add any other right side because of this reason, and I just stop here. That's a question. Okay, if I can't move any further, nothing else added to this set, then I stop there. That's the end. That's the end point. That's what we mean by the closure. Given A, I close on A. This is the closure set. Okay. If I take A and B, I start with A and B. Now you can see the left hand side is matching A and B. Now from this I can infer that these two actually control or functionally determine C. Okay. Now I add C into this set. Okay. Now if I add C into this set, now I can see that C determines the functionally determines D. Then I add D into this. After I add D, D determines A, but then A is already in the set. There's nothing else to add beyond that. So the closure of A and B attributes is A, B, C, and D. Okay, which is the full set of attributes of R. Okay, R has A, B, C, D. Okay, it's a full set of attributes. If you take A and B and compute the closure and you get the full set of attributes of the relation, then we call such an attribute set on the left hand side as a key to this relation. Why? Because A and B functionally determine all other attributes which are in the relationship. AB determines A, B, C, D relationship. Okay. Now, such a functional dependency, such a set can only be the part of the key. That because this uniquely identifies the whole tuple belonging to this relationship. Okay, right? And if you just take A, that is not any subset of this is not going to be key because the subset will not produce the full set of attributes that are part of the relation R. Okay. Similarly, the closure of BC here, you can see you take B and C attributes and try to close B and C. You start with B. Okay. C is already there. You start with C. If you, C is in this set, right? C, start with C. Then D actually can be added here. Okay. Right. Now, once you have added D, D determines A. A can also be added. So you can see that the closure of BC is B, C, D, and A. Hence, C is also key because this is a full set of attributes of relation R. Similarly, you take B and D. Okay, right? D determines A. So A can be added into this set. Okay, once you have A, a part of this. AB now determines C. So you also have BD is as a key, is also a key for this relationship. Okay, all super keys not in B, C, and F, since C and D are not super keys. Here you can see C and D from this exercise that we did. This relationship R, B, C, D, given these FDs, is not in B, C, and F because C and D cannot be keys for this relationship. Okay, C and D alone will not determine A and B, and hence C and D and A cannot be part of this. Cannot actually be. This relationship is not B, C, and F because of this requirement that every functional dependency, the left hand side has to be a super key. Now, given a set of relations and given a set of FDs, you can determine what is the whether the relationship is in B, C, and F. So this is the way you're going to do that. Okay. You will start with a set of attributes, compute the closure. If the closure actually gives the complete set of attributes in the relationship R, then we are going to call that as a key for the relationship. Okay, now you can see there are three keys for this relationship. C and D are not the keys for this relationship, or super keys which contain the keys, and hence this is not in BCNF. Okay, you have algorithms for the closure and all that stuff. I'm not actually going into uh, those parts. Okay, right. So let me play this. I'm almost reaching. Right. Okay. Now I'm going to go into little deeper. Okay. Up to this, is this clear, or you have any questions? Let me go. Okay. Let me ask before I go on to. Are there any questions? I'll just do one more thing, the dependency preservation, and then stop there. Okay. That's about no. That's the probably I will. I'm already reaching 3:16 now. Okay. If you have any questions, please let me know. Okay. I'll share these slides. If there are no questions, I will move on. Okay. Okay. Um, see, this is very important when for getting the BCNF. If you want to split a relationship, okay, it's possible that the one which you had split is in BCNF, but it could actually violate a functional dependence that is originally defined on the relation R. Okay, right? I'll just do this and stop there and come back in the next class to actually, you know, now I will do the 3NF and then 2NF and then 1NF. Okay? Right? That's what we're going to do. Okay. I'll just discuss this dependency preservation. Okay. And then say and show you why BCNF could be violating the dependency preservation requirement. Okay. Right? And then stop there. And then next class I'm going to show you if you get to 3NF, this problem doesn't come. So in some cases, third normal form is the best normal form, not BCNF. Though BCNF is the best normal form that you should be having for a relation, it's not always advisable to make all relationships into BCNF. Okay, Boy's card normal form. Okay, you will stop at 3NF. Okay, then for quickness sake, I will also do 2NF and 1NF. Okay, and solve some problems to show how we will basically look at normalization as a total concept with a set of problems that I will solve in the next class. Okay, I'll just do this dependency preservation and show you why BCNF could be a problem when we want to actually look at dependency preservation. Okay. For example, consider this relation R, A, B, R with C set of attributes A, B, C with the following functional dependencies. A and B determine C, C determines A. Okay. Now, if you take the closure on AB, it completes. So there is a key, right? There is a key called AB here. There's no other key. There's only one key, which is AB. Okay. Because if you take C, the closure doesn't, C will get A, but then doesn't include B. Okay. Right. So A and B is the only key in this relationship. This is not in BCNF because C to A violates the BCNF requirement that C is the C is not a key to this relationship. Okay, C is not key to this relationship, super key to this relationship, violates the BCNF requirement. Hence, not in BCNF because C is not a super key. To make it into BCNF, if we split this relationship into R1AB and R2 into A and C, okay, then we get into the problem of preserving this dependency. A, B together will determine the C. Okay, it's not just now this relation has only A and B. Okay, and this relation has only A and C. Independently, they are in BCNF requirement. Okay? But then the original dependency that is specified on this relation R, A, B, and C, that A, B determine the C is lost by the split. Okay, right? Which can only be ensured in R but not in R1 or R2 separately. You can't take R1 and then ensure that this dependency is preserved. A, B together will determine the C. Okay, right? So if you want to actually make this relation RABC into BCNF and split this relationship R1 into R1 and R2, you will end up actually losing this dependency. You won't be able to preserve this dependency. A, B determines the C. This is an important requirement that A and B together will determine the C in my domain. Now that is lost. So this probably is not a good idea because you don't want to lose this dependency. In your data, you want to have this dependency. A, B together will determine the C. And hence, though you got these relationships in BCNF, this is not a good thing to do because you've lost in the process the dependency preservation. Okay, so it's possible that BCNF doesn't preserve the dependencies, and hence not that you want to make every relation into BCNF. Okay, this is where you get into the notion of third normal form. What does third normal form do? Third normal form ensures dependency preservation but causes some duplication of data. We'll see how actually. What is the requirement of 3NF? A relation is in third normal form if LH of FD, functional dependency, is a super key. This is the same as the BCNF requirement. But if this is not done, it relaxes this requirement, putting an R condition. The RHS of the FD, functional dependency, is to be part of some key. So the RHS, if it is part of some key to the relationship, then this requirement is relaxed. Okay, so we say that the relation is in 3NF if one of these conditions is satisfied for all FDs. Then we say the relationship is in third normal form. Look at the previous one, okay, which we had actually looked at, R, A, B, and C. Okay, the FDs is AB determines C, C determines A. Now AB is the key. Now is in 3NF because the C to A, C is not a super key. If this is not satisfied, the other R condition is the right hand side is to be part of the key. Now A is of this key AB. Okay, so this now is in 3NF because one of these conditions have satisfied. Either the left hand side has to be a key or the right hand side has to be part of a key. Okay, that is a requirement for third normal form. Okay, R is not in BCNF, but R is in 3NF. Okay, so this preserves the dependencies. The AB dependency is preserved, and then this causes some duplication of data. For example, C to A, this functional dependency suffers from duplication of data because of 3NF suffers from this duplication of data. Okay, BCNF requirement that every functional dependency is reflected as a key constraint, as a super key constraint, ensures that there is no duplication of data. But it can result in the process losing these dependencies. For example, in this particular relationship, by splitting it, we lost this requirement. Okay, we lost this requirement that AB together will determine the C. So the dependency preservation is lost. Okay, so because of this reason, we will say this is a good thing to do. We don't go to BCNF. As far as this relationship is concerned, we are happy with 3NF. We don't want to do BCNF because we want to have dependency preservation. We don't want to go to BCNF. We'll stop at 3NF. Okay, third normal form. Though there is some problem that I am actually suffering from duplication of data, I'll put up with it. Okay, because by going to BCNF, I'm actually destroying this dependency. This dependency is not preserved by the split of this relationship into BCNF. Okay. Here is a when to stop with 3NF. Okay, right? When to stop with 3NF. Okay, when you want to have the dependency preservation and BCNF can cause loss of dependency preservation, you will stop with 3NF. You are not going to go with BCNF. Otherwise, for all relationships, you will get to the BCNF. Okay, because BCNF will avoid all kinds of duplication. Every relation you want to make it into BCNF. Okay, but in the case where you are going to lose dependency preservation, you are not going to go with that. I'll give you one example here. Okay, and then stop here. Okay, and come back and then do the other two normal forms and then continue. Okay, right. I'll take another. Here is a case. I have a ration card record. Okay, then I have a ration card number. Then I have a name, and I have a PAN card number. That means this ration card number is the number that the supply department, public supply department will give. Name is the name of the person, and the PAN card is the PAN card of the person. That PAN card of the that name of the person. Okay, right? PAN card. PAN card is the income tax card. I hope everybody knows this, right? PAN card and then ration card and now what is the thing in my domain? Each person can have multiple ration cards, such as ration card for kerosene, ration card for sugar, etc. That means one person will have multiple ration cards. That means he'll have different ration card numbers. One ration card number for kerosene, one ration card number for sugar and things like that. Okay. Multiple people can be associated with a ration card. For example, these are all family cards. Right? Given a card number, there could be multiple people that could be belonging to one ration card number. Okay, the whole family, each of those names will appear. Okay, given this, what is the key to the relationship? The ration card number and name will not get repeated. This will never get repeated. You will have a ration card number plus name is going to uniquely identify this ration card record. Okay, right? What are the functional dependencies? Ration card number and name will determine the PAN card number. Okay, right? Given that these two, they will determine the PAN card number. Okay, what is the functional dependency to a PAN card number? You can determine the name. Okay, right? Because the PAN card number associated with that, once you have a PAN card number, the name will agree. Same PAN card number, the names have to agree. Okay, given a ration card and a particular name, they'll agree on the PAN card number. These are the two functional dependencies. This relationship is not in BCNF since PAN card number is not a super key. This side of the relationship is not a super key. Their name and their PAN card. So PAN card can get repeated. Okay, same person having different cards, one for kerosene and one for sugar. There will be different card numbers, but the same person with the name. But once the name is there, his PAN card will be the same. Okay, right? But then PAN card here is not a key for this relationship because it gets repeated, not in BCNF. Okay, this is in 3NF because if you look at name, the PAN card, see the right hand side of this functional dependency is part of the key. Okay, ration card number and name. See this right hand side is part of the key and hence it is in 3NF. In 3NF, since name is part of the key, but not in BCNF. Okay. This relation will suffer from duplicate information due to PAN card and name dependency. Okay, because of this dependency, this name and PAN card will get repeated in this relationship. But then preserves the dependency that even a ration card and a name, the PAN card also is determined by the ration card and the name. Okay, so this is in 3NF and preserves this dependency. Okay, but then suffers from this problem of duplication of the data relating to PAN card and name. Okay, right. So this is where we are going to stop today's lecture. Okay, right. Um, what we have seen is we have seen the BCNF requirement. Just know give you the gist of what we have done. We have looked at a relation and we have actually defined when the relation is going to be in BCNF. Okay, and then we also showed what happens in relations where BCNF requirement can actually violate the dependency preservation, and why we would like to stop at 3NF itself, not go up to BCNF. Okay, and define the requirement for 3NF. So at the end of this lecture, I expect that given a relation and a set of FDs, you should be in a position to say whether the relation is in BCNF or is in 3NF. Okay, we'll do some example problems. We'll do more problem sets. Okay, we'll take some more problems and then see how to determine whether relation is in BCNF or 3NF. But this is something that I want you to understand fully as far as this part is concerned. Okay, normal form is concerned. Okay, yes, we will continue in the next class and we'll stop here. Okay, yeah, okay, right. Okay, I think we will stop here, and I think I've already crossed 3:30, so I'll basically come back